फटाफट लोन चाहिए? पैसाबाजार.com पे सबसे कम ईएमआई वाला लोन चूज करो, 2 मिनट में लोन अप्रूव। फटाफट लोन चाहिए? पैसाबाजार.com पे सबसे कम ईएमआई वाला लोन चूज करो, 2 मिनट में लोन अप्रूव।
Okay. Okay. Who are there? Niranjan, Bharat, Andrew. All of you, please type in your name so that I will get your attendance. Who all are there? Devdas, Shinoy, HSR 11 guys. Lakshya, Sriram, Brinda. Akarsh, Ketan, Ved, Omkar, Advait, Abhyay, Ashutosh. Okay, so hello everyone. Today we are going to start a new chapter, and that is isomerism. Okay, this is the second chapter for organic chemistry we have of organic chemistry. So like in HSR 11th, I have finished nomenclature, and that I will finish tomorrow in Rajaji Nagar. Okay. But we have done a little bit of nomenclature in Rajajinagar also, so that you can correlate or understand the facts of that we use in this somewhere we use in this particular chapter of isomerism. Okay, so all of you have the basic idea of nomenclature, so I don't think you will feel much difficulty into this. But yeah. So we'll start this chapter, isomerism. Okay, see, this chapter is again it is important and difficult, I would not say, but it is interesting, right? You can understand this chapter, and then because in daily day-to-day life also we have a lot of application of isomerism. Like we do not use, but all these pharmaceutical industry, if you see, whenever they produce any medicine and all, they first try to understand the stereo aspect of one particular compounds, right? Organic compounds, because when the structure of the organic compound changes, its physical and chemical properties changes, and that is what isomerism is. Okay, so first of all, you see, isomerism is what? Isomerism is a phenomenon. Okay, isomerism is a phenomenon in which one like one particular molecule with one particular molecular formula can be represented in two or many other different ways, right? And all these different structure that you can draw from one particular molecule gives you different physical or chemical properties of the same molecular formula, right? So first of all, if you see the definition of this particular term, that is isomerism, and before understanding this isomerism, first of all we should write down, or we'll write down the definition of isomers. Okay, so all of you write down the definition of isomers. Isomers are two or more compounds. Isomers are two or more compound having same molecular formula, having same molecular formula, but have different physical, have different physical or chemical properties. Chemical, physical or chemical properties. So two or more compounds having same molecular formula but different physical or chemical properties are known as isomers. Okay, and this phenomenon is called isomerism. Is called isomerism. Okay. So, and what kind of phenomenon? Phenomenon of existence of one particular molecular formula into two or more different structural formula. That phenomenon we are talking about, right? No, we have just started, Ashutosh, so you did not miss anything. Neha, Sharanya, Avve. Okay, so we have just started, so you did not miss anything. So isomers are what? Two or more compounds having same molecular formula but have different physical or chemical properties. And the existence of two or more structural formula of the same of one molecular formula is known as isomerism. Okay? Like suppose if I take one example here. Suppose if I write CH3 CH2 OH. And one more molecule if I write, which is CH3O CH3. Right. So this is what, if you see the molecular formula of this, we have two carbon, so C2H6O. Right. And for this one, it is again C2H6O. Right. Molecular formula is this. Now here you see this is an alcohol and this is an ether. Obviously, alcohol and ether are two different functional groups, so they have different physical or chemical properties. Okay, so that is why you see this two molecule are called isomers of each other. Isomers, you see, isomers is only defined for a pair of molecule. This term is only defined for a pair of molecule. When I say isomers, it means we are talking about two molecules, not single molecule or one molecule. Okay. So this ethanol, the name of this one is what? Ethanol, and this is dimethyl ether or methoxymethane. Okay. Ethanol and this are said to be isomers of each other. Why? Because they have same molecular formula but different physical and chemical properties. Why different physical and chemical properties we have? Because we have two different functional group here, right? So that's the thing. There are many other examples that we'll see one by one. Okay, this is just one example I have given you, right? So isomers is always defined for a pair of molecule. If you say this is isomer, if you say compound A is a isomer, that does not mean anything. Isomers is always defined for a pair of molecule. Okay. Now in this isomerism, the classification of isomerism is the next part that we have to understand, right? And then we'll see various example in various different types of isomerism, right? So classification of isomerism, you see, isomerism. So there are mainly two types of isomerism. First of all, The first one is structural and the second one is stereo. Structural isomerism or stereo isomerism. Okay, stereo isomerism again classified into two categories, that is configurational and conformational. Configurational and conformational. Configurational isomerism again classified into two categories, that is optical and geometrical. Optical and geometrical. Structural isomerism also classified into 5-6 categories. Structural isomerism, you see, it is also classified into 5-6 categories that we'll see one by one. The first of all, the first type of structural isomerism we have chain isomerism. Second one we have position isomerism. Third one we have functional isomerism. Fourth one we have metamerism. META, metamerism, right? Functional, we also one type of isomers in this we have, that is ring chain. Okay, that we'll see also. And the last one we have here, that is tautomerism. Tautomerism, right? So here you see in this chapter we have to study structural, we have to study conformational, we have to study optical, we have to study geometrical. All these four things we have to study. And in this, the first part, which is the structural isomerism, it is the most simple one. Most simple one we have out of all these. Okay. But everything is important, right? Optical, geometrical is the most important part in this chapter we have for JE point of view, right? This one is the simplest part that will start with structure only today. Okay, conformational and optical also we'll see. So all these things one by one we have to study. Okay, in this what happens in structural isomerism, we usually say the connectivity of atom is different. I'll just write down in the next page. Here the connectivity of the atom is different. Here the connectivity of atom in the space is different. We are talking about three-dimensional molecule here in case of stereoisomerism, right? In the space, if the arrangement is different, then we call it as stereoisomerism. Okay, so first thing that will start here, that you write down is structural isomerism. Last two parts of structural is metamerism and tautomerism. This is metamerism and this is tautomerism. Okay, metamerism and tautomerism. One more thing I forgot to tell you here. See, this tautomerism we will not discuss now because it requires some concept of reaction, how the reaction goes. It is actually a kind of isomerism in which two molecules are exist in equilibrium. Okay, so this tautomerism part we will not discuss now, right? This will discuss later on, not today, right? When we study some basic concepts of reaction mechanism, in that we'll discuss this tautomerism, especially in GOC, right? So next thing you write down, that is structural isomerism. Just a second. So thing is. Just a second, I'll start. Okay, structural isomerism. Write down the definition here for structural isomerism. This is the type of isomerism in which the connectivity of atoms or groups are different. Okay, then essential condition is what is that, Bharat? What is PT groups? Ring chain is also a classification that comes under functional isomerism, Shreya. Okay, see, ring chain also we'll discuss in this particular section only, but that comes under functional isomerism. I'll mention this later on. Understood, Shreya? I'm not getting you, Bharat. What do you mean by this point groups? Okay. Chalo, see, connectivity of atoms or groups are different. You see, like the first thing here, for a compound, for any compound to show or to have the relation of isomers, they must have same molecular formula. Molecular formula must be same. That's the essential condition we have. If the molecular formula is not same, it means those two compounds are different compounds. They are not identical, right? So whenever we are talking about two compounds, suppose A and B, and if we try to establish the relation between these two compounds, relation means what? Whether these two compounds shows isomerism or not. If they shows, then what kind of isomerism they show, whether it is chain, position, functional, whatever, right? So to establish or this kind of relation, the first thing we should have that they must have same molecular formula, right? If they do not have same molecular formula, the compounds are different, then we cannot say that they exist or they have isomer relation or something like that. Okay, now in this you see structural isomerism, the connectivity of atoms and groups are different. Meaning here it is what? Suppose if I write down this compound, A is connected with B, B is connected with C, and C is connected with D, right? Molecular formula is what of this compound? It will be ABCD. I'm taking some general example. ABCD, right? Now if I write down the another structure of this in which we have A connected with C, connected with B, and connected with D. For this one also the molecular formula is ABCD only, right? So you see the molecular formula for both compounds are same, but the connectivity is not same here. Connectivity means what? You see here in the first particular example, A is connected with B only, and B is connected with A and C. C is connected with B and D. right? But when you compare with this compound which has the same molecular formula, A is connected with C is connected with A and B is connected with C and D. You see here B is connected with A and C here, and here it is connected with C and D. So obviously the connectivity in these two molecules are different, and that's why we say that there is a phenomenon of structural isomerism possible. Okay, structural isomerism possible. Now, like I told you that there are 5, 6, 7 types of structural isomerism we have. Those are chain, position, and all, right? So one by one we'll discuss this, because in the exam they ask that which of these molecules shows chain isomerism or position isomerism. Okay, so the first uh, part of it, structural isomerism, you write down. The first type of structural isomerism is chain isomerism. Chain isomerism. Now, like I said, that to show isomerism, the molecular formula must be same. Now, we are going to discuss chain, position, function, and all. So, how do you identify that the given compound shows chain, position, or functional isomerism? To understand that, first thing that you should know that for that to show chain isomerism, what is the similarity we should have between the two organic compound, and what is the dissimilarity we should have? These two information you must have, right? The first thing is what, which is common in all type of isomers, whatever we'll do, whether it is structural or stereo. The first thing is what, that the chain isomers should have same molecular formula, and this thing is common in all types of isomers. Any compound to show isomerism, they must have, any two compound to uh, show isomers, they must have same molecular formula, right? The first thing is this should be common, and for to show chain isomerism, they must have same functional group also, same functional group. And the third thing that you should know, which is different carbon chain. Different carbon chain. What do you understand by different carbon chain? The number of carbon atom in the parent chain must be different. That's the meaning. Okay. Different carbon chain means what? The number of carbon atom in the parent chain should be different. For example, you see if I write down this molecule CH3, CH2, CH2, CH3. What is the name of this compound? N-butane, right? It is N-butane, or simply butane IUPAC if you want to write. What is the molecular formula of this? Suppose if I write down one more compound here, which is CH3, CH3, and CH3, right? This is 2-methyl propane. 2-methyl propane. See, like this, if you do not write this name also, it's fine, because we are not doing nomenclature here. But in this organic chemistry, you always get this kind of compounds in all the chapters. So this nomenclature you can practice parallelly. Whatever compound is there, you just try to write down the name of that. So you don't require any. So you don't have to go for separate, practice session for nomenclature, right? Whatever chapter you are doing, you try to write down the name. That is how you can practice nomenclature. Anyways, coming back to this, can you tell me the molecular formula of this? It is C4H10. Does these two compounds have same molecular formula? Yes or no? These two compounds have same molecular formula, yes or no? Tell me. right? Molecular formula of this compound is also what? C4H10. You see, this is the first and essential condition for any two compounds to show any kind of isomers, right? You see, same molecular formula, but number of carbon atom in the parent chain. You see, here it is how many carbon atom? Here it is four, right? Straight chain, and here the number of carbon atom in the parent chain is three only, right? Three only. So you see here, same molecular formula. There is no functional group and different carbon atom present in the parent chain. So these two compounds are the example of what? Chain isomers. Right? So what we call it as N-butane and 2-methyl propane are chain isomers of each other. And this phenomenon is chain isomerism. Is it clear? Tell me quickly. Okay. See the another example here. Here we have OH and OH and CS3. What is the relation of these two? Means what kind of isomers it shows? See here also you try to compare this. How many carbon atom we have here? One, two, three, four, five. The name of this compound is what? 2-pentanol, right? It is 2-pentanol. The name of this will be what? One, two, three, four, right? 2-methyl butane to all, right? So again you see here molecular formula of this is what? Excuse me. Molecular formula is 1, 2, 3, 4, 5. So it is C5H H12O, I guess, right? And for this also the molecular formula is sorry C5H12O. The molecular formula is same and the functional group is same. Number of carbon atom in the parent chain is different. So this is also the example of chain isomers, right? See, there is one more thing here, like, and this thing you listen to me carefully. Sometimes it is with few examples, it is sometimes difficult or confusing to understand. Like this, everything you have to check. So to do this, whether it is chain or position isomerism that we'll discuss after this, what we'll do, we calculate isomeric number. So this is a trick we are using, right? And the trick is what? We will calculate isomeric number. Isomeric number. Now, what is isomeric number? It is XY. Isomeric number is XY. Now, what is X? Write down. X is the number of carbon atom in the main chain. Number of carbon atom in the main chain. And Y is the number of carbon atom. Okay, the Y is the number of side chain. The number of side chain starting with carbon. With carbon. So what you have to do, just you can find out X and Y and you write it down there. Okay, like you see here. For this compound, and the thing is what? For chain isomers, this also you write down. For chain isomers, the number of the isomeric number must be different, right? If the isomeric number is different for the two compounds, with provided what? Provided they must have same molecular formula, right? With same functional group, right? So if the isomeric number of two compounds, provided they have same molecular formula and functional group are same, then those two compounds are known as chain isomers, right? Now how do we find out this isomeric number? You see in this one, for this the first one n-butane, if this isomeric number xy you have to find out, what is the value of x here? The number of carbon atom in the main chain, that is 1, 2, 3, 4. We have x value is 4 and there is no branch present into this, so y is 0. So isomeric number of n-butane is 40. Is it clear? Is it clear how do we calculate this isomeric number? If not, then you can ask me. Right. So you tell me what is the isomeric number of this compound? Tell me the isomeric number of 2-methyl propane. Who is this VG plays? Please type in your name. I will the use I will tell you, Krishna. Wait. Okay. So the value of X is the number of carbon atom in the parent chain. That will be 1, 2, and 3. So we have 3, and there is one side chain starting with carbon atom. That is important. You see, number of side chain starting with carbon atom. Right. So that will be 1. So XY value is 1. So now you see when you have this isomeric number, right, and the two molecule has same molecular formula, this is what you have to check. The molecule must have same molecular formula, right? So two molecules having same molecular formula and different value of isomeric number, which is xy. So when the two molecules having same molecular formula and different isomeric number, they're said to be chain isomers. Is it clear now, Krishna? You will feel like, okay, why this thing we are calculating, we can directly look at the molecule and say, right, whether it is chain isomers or not. Yes or no? How many of you are thinking this? How many of you are thinking this, that we don't require this, we can look at the molecule itself, just we check the number of carbon atom in the parent chain, and then we can say it is chain isomers or not? How many of you are thinking this, that this isomeric number is not required? Type in fast. Okay, so whatever you are like, whoever thinking this, that this is not required, just give me some more time. You will understand the uses of this, because these are very simple compounds. Okay, the example that I have taken here, right? Yeah, fine. These are very simple compounds actually. So in the exam they won't ask you these compounds, but for other compounds I'll give you the examples. There we have this thing is useful, isomeric number. Okay, that's why we are doing this. Anyways, so we'll do that. Tell me the isomeric number of this compound. These two. Tell me the isomeric number of this fast. Sushant, it won't be difficult later if you understand it properly. At least this part, structural part, is easy. Okay, so for this one, the value of x is 5 and there is no side chain starting with carbon, right? So y value is 0. So it is 50. And for this one, xy value is 4 is the value of x, and for y the value is 1, 41. Do you see? Two different compounds with same molecular formula, same functional group, having different isomeric number, hence they call it as what? Chain isomers of each other. It's okay, Devdas. Okay, 50 and 41. So these two are also chain isomers of each other. Fine. Can we move on now? Next thing. Okay. Next, the second type of structural isomerism we have, that is position. Position isomers. Okay. Now in this you see again, what is the, for two compounds, what is the condition we have to check to understand whether they are position isomers or not? That is what I'm not giving you the definition here. Definition you will get it in the book, but that won't help you in solving the question. So the key points that is required to identify whether the molecules are position isomers or not, that I am giving you. The first thing here you have to write down, here you write down the two molecules, if they have same isomeric number, same isomeric number, then they are said to be position isomers, right? Same isomeric number you should have. Now, what is the similarity we should have in the two compounds? The first thing is again the same molecular formula. They must have same molecular formula. They must have same functional group. Same functional group. Third one, we have same parent chain, means the number of carbon atom in the parent chain must be same parent chain. And the last one, different location of, different location of double bond or triple bond, functional group if it is there, functional group or substituents. Welcome, Sukirth. Anyways, so different location of the substituents, right? Double bond, triple bond, functional group, or any substituents. Okay. So these are the four condition we have for position isomers. Okay. And apart from these four, one thing that always helps you a lot in finding out position isomers, that is same isomeric number. Now you see the example here. If I write down this one, what is the name of these two compounds? I guess all of you can write down the IUPAC name. You see the molecular formula for both the compounds is same, C4H9Cl, right? C4H9Cl. See, same parent chain, when you say Advait, it means we should have equal number of carbon atom in the parent chain in two different molecule. Means number of carbon atom in the parent chain you cannot change. Otherwise, it will be chain isomers, not position isomers. You see here also one, two, three, four. Here also one, two, three, four carbon. Okay. Same number of carbon atom in the parent chain for two different compounds with same molecular formula, and only the position should be different. Here you see, if you try to write down the name of these two compounds, we'll check the parent chain is this, and then we numbering this one, two, three, four. For this it will be one, two, three, four. The name of this will be what? 2 chloro butane, right? And for this it will be 1 chloro butane, right? So in these two compound you see molecular formula is same. The only difference is what? That the position of chlorine is different. Okay. So position of chlorine is different. So it will be what? It will be chain isomers of each other. Now you tell me the XY, the number isomeric number is what for these two molecule? You tell me the XY of this and XY of this isomeric number. That will be what? 4 carbon, so 40, and 4 carbon, so 40. You see the two molecules have same isomeric number, and hence they are position isomers. Another example you see, these two. You see the position of double bond is different. If you write down the numbering here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, the name of this will be what? It is pentene, pent 1 ene, or simply pentene. And this one is what? Pent 2 ene, right? So position of double bond is different. If you find out the isomeric number, that will be 50 here and 50 here. So isomeric number is same, molecular formula is same, hence the compound is what? Position isomers. One more example you see, if I write down CH3, CH2, C triple bond CH, and CH3, C triple bond C, CH3. You see the molecular formula of this is what? C4H6, and it is C4H6. Same molecular formula. Only the position of triple bond, here it is at first carbon and here it is at second carbon. If you find out the isomeric number, that will be 40. Isomeric number, that will be 40. Same isomeric number, positional isomers. Right? If there are two functional group like OH and Cl in two different compounds, only the location of Cl in the first. See the compound. See the compound. Let me give you one example here. Like this, you will get confused. See, if you have this compound 1, 2, 3, 4, 5, you have chlorine here, right? And another compound, if you write 1, 2, this, and if you write down chlorine here, see, these two compounds are what? They are isomers of each other or not? They are isomers of each other, is not or not? Are they isomers of each other? What relation they have? Any one of you, can you tell me the name of this compound? And what is the name of this compound? See, the two compounds will be same or different depending on their name. If the name is same, the compound is same. You see, for this one, if you write down the first one, it will be 1, 2, 3, 4, 5, and 6. So it is 2-chlorohexane. Correct, Bharat? 2-chlorohexane. And for this one, if you write down the numbering 1, 2, 3, 4, 5, 6, this is also 2-chlorohexane, right? 2-chlorohexane. So basically, these two compounds are identical compound. They are not isomers of each other, right? So whether the two given compound is different or same, that depends on their name. If you write down one more compound like this, see 1, 2, 3, 4, 5, 6, and if chlorine is here, then this is 3-chlorohexane. So this one and this one are position isomers of each other because it is 2-chloro and this is 3-chlorohexane. Only the same substituents in both compounds cannot be the same position in the same position, but different substituents can be in the same position. Like, see, we'll see the position of chlorine and hydroxy group separately. No, if you have one OH group is present at second position, if see that there are only two things. I'm not actually getting you, Ashutosh, properly. But if you have any doubt in whether the compound is same or different, if the name is same, then the compound is same. That's the only thing. Whatever the two compound you have, with the position, you write down the name of that compound. Right? If you're getting same name with same position of substituents, then only it will be same. Yeah, you better you ask me in the class. Okay, chalo. So you see some examples I am giving you here, and you have to identify that whether they are chain or position isomers. Okay. So one by one, I'm writing it down. You just tell me once you finish it. The first one is, just a second. Hello. Yeah. Yeah. Smita, can you call me tomorrow or after 7:30 because I am busy in the office now. I'm in a meeting. Yeah. 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 Same number. You can WhatsApp me. Oh. Okay. So the compound is this. This one. This There is one methyl group here, right? And this one. Tell me. First one. Yeah, just you write down the name, whether chain or position. Same position, chain position, 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 position. Okay. You see this one and these two, both compounds are same. The isomeric number of the first one is 41 and the second one is also 41. But the compound is identical. They are not isomers of each other. This is also 2-methyl butane. This is also 2-methyl butane. Okay. So the XY value is same and the compound is said to be identical. So you must take care of one thing. When the isomeric number is equal, then you have to check that whether the compound is identical or not. If not identical, then it is position isomers. Okay. So these two compounds are identical. Again, this one you see, for what is the value of isomeric number for this? Is it 32? And for this it will be 32. Same number, 3 carbon in this ring. The parent chain in this is what? Will be this ring, 3 atom, and we have 2 side chain with carbon. 2 side chain with carbon. So XY is 32, and this is what? This is positional isomers. This is positional isomers. For this one, XY value is what? 41. Sorry, XY value is 51, and for this XY value is again 51. Position of this methyl group, you see the number of carbon atom in the parent chain is 5 and 5. X nothing but the number of carbon atom in the parent chain, right? So 5 and 5 is equal. Position of this methyl group is different. So this is also positional isomers. What about this one? This one is also, you see, if you write down the name of this, its XY or isomeric number will be 40, and its isomeric number will be again 40. This is cyclobutene. This is also cyclobutene. So the molecules are identical. This one you see, this one, the numbering will be like this: 1, 2, 3, 4, 5, and 6. And for this, it will be 1, 2, 3, 4, 5, and 6. XY isomeric number for this compound is what? 60. Isomeric number for this compound is 60. Equal isomeric number but different position of double bond. Here it is at between 4 and 5. Here it is at 3 and 2. 3 and 4, right? Different position of double bond, same isomeric number. Example of position isomers, right? In this one, what is the answer of this one? Tell me, for this question, what is the answer? What is the name of this compound? So only RM1 is correct in this. You see, here the numbering will start from this carbon 1, 2, 3, 4. And here the numbering will start from this carbon 1, 2, 3, 4, and 5. So here we have 5 carbon atoms in the chain. And here we have 4 carbon atoms in the chain. The name of this will be 2-methyl butane nitrile. And for this will be pentane nitrile. Okay? It's not cyanobutane. Have you, RNR guys, have you finished this nomenclature of cyano group nitrile? Yes or no? Have you finished this nomenclature of cyano group? Oh, that's why you are wrong. Anyways. So you understand one thing, when you have cyanide group present, then we always start numbering from this carbon atom of the functional group. We'll discuss this tomorrow also in the class. Yeah, it is a functional group. So for this functional group, we always start numbering from this carbon. That is the rule we have. Yes, cyano group C is counted in the chain. So 1, 2, 3, 4. We start from here and try to get the longest possible chain. So here we have 4 carbon, here we have 5 carbon. Number of carbon atom in the parent chain is different. Molecular formula is same. So it is a chain isomers. Okay. Now for this one you see molecular formula is same. The value of isomeric number is 40, and here the value of isomeric number is again 40. Oh, it's 50, right? And this is also 50. So it is position isomers of each other. Position of OH group is different. What about this one? What is the value of XY? 61, XY 61. Same isomeric number. We'll start counting, numbering from this carbon 1, 2, 3, 4, like this we go. And here we'll start from 1, 2, 3, and 4. Right? So the position of double bond is different. Here it is at third carbon, and here it is first carbon with equal isomeric number. So it is position isomers. Yes, Bharat. Where is nitro? Sriram. Where is nitro? There is no NO2 group present. It's OH, hydroxy. Done? All of you done? Okay, I'll tell you tomorrow. Nitro is NO2. Okay. Okay. Few more examples we'll see. See, in this one, I'm giving you three structure, which is this first one. This is A, B, and C. What is the relation of AB? A and B, what is the relation? A and C, what is the relation? B and C, what is the relation? Okay, so position, chain, and chain. You see, what is the isomeric number of this one? A, XY. It is 62. This is 62 and XY is 61, right? So AC and BC are, these two are chain isomers, different isomeric number. AC, BC has different isomeric number, chain isomers. AB is position isomers, right? See, we have two substituents into this, two functional group. What kind of isomers these two are? Or they are isomers or not? Are they isomers? If yes, then what kind of isomers? What is the molecular formula of this? 1, 2, 3, 4, 5, 6. 6 carbon, right? So C6, 3, 4, 5, 6, 7, 9 plus 3, 12, H12O. This is the molecular formula. For this one, it is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C6H12O, right? Same molecular formula. Molecular formula you must check, right? So when you write down the name of this compound, you will start numbering from the left carbon because OH we have to give the priority. So we'll do from 1, 2, 3, 4, 5, and 6. And this is 1, 2, 3, 4, 5, and 6. You see the name of this will be hex 3 in and 2 all, and this E you have to drop, and here we'll write hex 5 in 2 all, and this E again you have to drop. You see the position of double bond is different, and hence it is a pair of position isomers, right? Two substituents is here. You can have any other chlorine also present here or here. Then also you will do in the same way. I hope you will understand now. Okay. In this one, what is the value of isomeric number? 60. What is the value of isomeric number? XY. 60. You see, same isomeric number, we have position isomers. Understood now? See, just you go through the name of this. First of all, if see the logic here is what? The first thing molecular formula must be same. Yes, it is same, right? XY value is equal, so equal. So that's why it is position isomers. If one substituents, the position of one substituent is same, but the position of other one is changing. So with respect to that, it is a position isomers. If it is same in both, then it will be identical compound. If the position is same, so both name will be same, identical. Okay. So now you see this one. This one and this one. What kind of isomers these two are? And after this, two more we'll see. I'll write down here the next two example. And the last one we have what about the first one? The first one you see, the molecule has same molecular formula. It is very clear from this. 6 carbon, and here we have 6 and 4, 10 carbon, 6 plus 3, 9, and 1, 10 carbon. So molecular formula is obviously same. That you have to check first, right? Molecular formula is same. What is the XY number of this isomeric number of this compound and isomeric number of this compound? In these kind of compound, we call it as bicyclo compounds. Okay, I will discuss this tomorrow in Rajinagar. This is bicyclo compounds. So in bicyclic compounds, it is easier to check this isomeric number. So in this, the isomeric number will be what? How many carbon we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total X value is 10, and there is no chain into this, so that is 0, 100. X value is 9 here, and there is one chain, so 91. Molecular formula is same, isomeric number is different, hence these are chain isomers, right? How it is chain, Sukir, the last two? This one you see, only the position of double bond is different here. XY value you can calculate, you'll get the same into this. XY value is what? It is 100, and for here also XY value is 100. Same molecular formula, equal isomeric number, it means it is position isomers. And clearly you can see from the molecule the position of double bond is different. For this XY value is what? It is 63, and for this it is XY value is 62. Different isomeric number. It cannot be position, it is chain. Understood now? So when you calculate this isomeric number, this will be easier to identify. Yes. Can we move ahead now? Okay. Next, write down. There is one kind of question that they ask, which is number of mono substituted product we have to find out. No, just you have to find out. You see, if you have to find out XY value, you only need the number of carbon atom in the parent chain, that is X, plus how many side chain or substituents we have starting with the carbon atom, right? So in the side chain, number of carbon atom you don't have to find out. You see this one. I'll go the previous slide once. You see in this one, we are not counting these two carbon here. We have just counted, okay, one substituent is this, starting the carbon. So this whole is one and this whole is one. So that's why 6 in this ring and 1 plus 1, 2. Here you see this whole is 1, 2 and 3. That's what is 63. I hope it's clear now. Okay. Next you see the number of one question that they ask into this, that is number of mono substituted product. You have to find out number of mono substituted product. Mono substituted product means what? Only one substitution is there. Means only one hydrogen is replaced by the any other element. Okay, so you see here, first of all, if I take the example of butane, and suppose butane is C4H10, butane is C4H10, right? So the question we have to find out how many monochloro products we get. Okay, and the question is with this compound, how many monochloro product forms? Means one chlorine you have to add into this molecule. One hydrogen will come out and one chlorine will attach onto that carbon atom from which the hydrogen is coming out. Try to find out this. Are you done? I can't see your comments. Just a second. Yeah. Okay. So answer is Advait is saying 5, Shravan 6 or 5. Tell me one answer, Shravan. And most of you are saying 2. 2 monochloro derivative. Sukirt, Areman, Bharat, Niranjan, Yashketan. Who is this Visi Place? Type in your name, please. Yashketan is saying 6. Oh, it's Gaurav. That's what I was thinking. Anyways, okay, you see, so butane we have. So, see, first of all, you have to understand, and okay, now I am explaining. Okay, someone is saying 5, 6, and all. Okay, first of all, you have to draw the structure of butane. CH3, CH2, CH2, CH3. This is one possible structure of butane, or we can also draw this structure. CH3CH, CH3CH3, isobutane. Sorry, right. These are two structure possible. Okay. Now, in this you see there are two different position we have. You try to understand this. Okay. There are actually two different position. We can add one chlorine. See, this carbon is what? This carbon is 1 degree carbon. This carbon is 2 degree carbon. This is 1 degree carbon and this is 2 degree carbon. So we can add chlorine any one of these two carbon atoms. You see the possibility here, it is what we have. One possibility is what? And here also there are two possibilities. This carbon is 1 degree, this carbon is 1 degree, this carbon is 1 degree, and this one is 3 degree. So any of these carbon atom, if you add chlorine, the product will be same. Similarly, here also, these two carbon atom, where you listen to me carefully, where you add, whether you add chlorine on this carbon or this carbon, the product will be same. Okay, so if I write down one of the product here, that could be CH3CH2, CH2CH2Cl. Yes or no? This is one possible product. And another possible product is what? These two carbons are identical carbon. So whether you add chlorine here or here, you will get the same product. So another product is CH3CH, CH2CH3, and here we have one chlorine. Okay. Now in this you see the two different product we can write here. That is CH3CH, CH2Cl, and here we have CH3. And the another one is CH3C, CH3, CH3, and here we have chlorine. Tell me, any doubt you have? Right. So here you see, we cannot, if you add chlorine here also, suppose I have added this chlorine here, when you add here also, you'll get the same product. Then the numbering will start from right hand side. Similarly, if you add chlorine onto this carbon atom, we'll start numbering from this side. So both product will be same. Yeah, I'll give you Sushant. First, you understood this one or not? You tell me. Correct. So in this question, the number of possible monochloro product is 4. The answer will be 4. Right? Now the second thing, what kind of isomers these two are? Coming back to the isomerism part, right? What kind of isomers these two are and what kind of isomers these two are? Tell me. Okay? You see how you can do this? This is chlorobutane, this is 2-chlorobutane. So obviously the position of chlorine is different. So these two are positional isomers. XY value, isomeric number you can find out. Here also you can isomeric number find out. This is 1-chloro, 2-methyl propane. This is 2-chloro, 2-methyl propane. Position of chlorine is different. These two are also positional isomers. Understood all of you this? See, in this type of question, they can ask you many. There are many permutation and combination here. They can also ask you how many positional isomers will get here. There are possibilities that some of the compounds will be position isomers and some of the compounds will be chain isomers, like that. Okay, so they can ask you how many compounds are positional isomers, how many compounds are chain isomers, what is the total number of product, also anything they can frame. Okay, so the total product, the answer will be 4. The number of position isomers is also 4 in this case, but depending on the compounds and molecules, the answer can be different also. Is it clear? Okay, this question you tell me. CH3, CH2, CH, CH3, and CH3 here, right? In this, how many monochloro product we can get? How many monochloro product we can get? Tell me, Sushant. Just a second. Give me a second, I'll start. Just a second. Okay, so what is the answer? How many products we get here? This carbon is 1 degree, right? And this carbon is 1 degree, and this carbon is 1 degree. So these three carbons are 1 degree carbon, and this one is 2 degree, and this one is 3 degree carbon. Now, when you see here, there are different group we have. So in this one, you see, if I add, I can add chlorine here, right? I can add chlorine here, or we can add chlorine onto this carbon also, or we can add chlorine here also, and at this position also, right? If you add chlorine to this carbon, then this carbon and this carbon is identical. But this carbon and this carbon is not identical, however, they are 1 degree carbon. You see here, the structure that we get, see the possible structure if I write down here, it will be CH2Cl, CH2CH, CH3, and CH3 plus another possibility is what? We'll get this CH3CHCl, CH3, CH3. Another possibility is what? We'll get this CH3CH2, CCl, CH3, CH3. And the last one is CH3CH2, CH2, Cl and CH3. Okay, so you see if you compare these two compounds, the name is different. This is 1 chloro, 1 chloro 2 methyl butane, right? And for this it will be 1 chloro, so 1 chloro 3 methyl butane. So name of these and these compounds are different. However, these two carbon are 1 degree carbon, but because of this CH3 present here, these two carbon gives you two different product, and the answer will be 4. Yes, most of you have said 4. Answer will be 4. Okay, so now the thing is, what you don't have to draw this structure every time in the exam. Like suppose in this one, the last one like this will do. Suppose the compound is this, right? And we have one methyl group present here, methyl cyclopentane it is. How many product possible here? Just you have to look at the molecule and say, you see this carbon, if you add chlorine you'll get one product. This carbon, if you add chlorine you'll get one product. This carbon and this carbon is identical, right? This carbon and this carbon is identical, and this carbon and this carbon is identical. So whether you add chlorine onto this carbon or this carbon, the product will be same, or this carbon or this carbon, the product will be same, right? So you see the answer for this one will be 1, 2, 3 and 4. Again it is 4. So like this, if you practice, you don't have to draw this product every time, right? By looking at the molecule itself, you can identify that at which carbon, if you add chlorine atom or any other derivative, you will get different products or not. Okay, so here also the answer will be 4. Is it clear? Now, next one you write down, the third type we have, that is functional isomers. Now again, the condition in this you have to check is this. For functional isomers, the first condition is same. That is same molecular formula. Molecular formula. No, Niranjan, no formula. Why you need formula always? For functional isomers, we must have different functional group. Different functional group. And when the functional groups are different, so they must have different chemical properties. So only one thing you have to check into this, that same molecular formula which is true in all cases, functional group must be different. Okay, that is the only. The first example that I have given you when I gave you the definition of isomerism, there I've given you alcohol and ether. So that example is an example of functional isomer, right? Those are functional isomers. So in this you see there are, this one is a bit important, there are different functional group we have which can show functional isomers. Okay, so that we'll see one by one. The first example in this is alcohol and ether. Alcohol and ether. Alcohol and ether with same molecular formula can show functional isomers. You see the example, the first example I have taken. CH3CH2OH and CH3OCH3. These two are functional isomers of each other. You see, molecular formula is same, but the functional group is different, right? Functional group is different. That's why these two are functional isomers of each other. Okay. Another example we can have here, you see, alcohol and phenols. Okay. Don't get confused with this. Alcohol and phenol also forms functional isomers. Like you see the example here. If I write down this compound, we have OH, right? It's a benzene ring, OH, and this one. Here we have CH3 also, and this one, CH2OH. This is alcohol. See, when this OH group is directly attached to the ring, it is then phenol. This one is phenol. When OH group is directly attached to the ring, see, isomeric number we only calculate for chain and position. Okay, not for functional. But for functional isomers also, if you see in this one, the isomeric number will be same. But that helps you more in case of this thing, chain and position isomerism. Okay, that helps you more over there. Here you have to check only the difference, or only different functional group you have to check here, right? So here you see, in this case, alcohol and phenol, you see, whenever, see, how do we understand that phenol and alcohol is there? Whenever OH group is attached to the ring directly, it is phenol, otherwise it is alcohol. Now these are the two. Why, how do we understand this? Because in this, the chemical properties of these two compounds is so different. Few we will discuss here, but we'll see this again when we discuss this in details in alcohol and phenol chapter, right? So here what we have, this oxygen, this is very difficult to oxidize, right? This group, when it is directly attached to the ring, but this oxidation of this is possible, comparatively easier oxidation we have. When this get oxidized, so that compound will be very unstable. So like this, there are various other chemical properties we have, and you see the molecular formula is same. That's why these two are functional isomers of each other. Okay, how do we understand phenol? OH group is directly attached to the ring. That you must keep in mind. It is CH2OH, not CS3. Okay, so alcohol and phenol, which uh, some of you must have doubt into this, that alcohol is also OH, in phenol also will write OH only, then how they form uh, functional isomers. Okay, so don't get any doubt, don't get any doubt into this. Okay, alcohol and phenols forms functional isomers. These two are important. Now third one, in this you see there are many functional group we have basically. Okay, so third one, you see, all these you have to keep in mind. Okay, phenol and ether also, when alcohol and ether forms functional isomers, so phenol ether may also form functional isomers. Okay, so you see here example I'll write down. Phenol is again the same example I'll take. Benzene ring, here we have CH3 and OH. And if I write down the another molecule in which the ether linkage is there, OCH3. Right. So this also, This is ether and this is phenol. So phenol ether, you see molecular formula is same. You can check the molecular formula. It is same. Third one you see, sorry, fourth one, amines. Amines. Okay. Two, three things are here. These are the derivative of ammonia. Derivative of ammonia. This slight little bit information I'll give you in a nomenclature tomorrow class. Okay. Ammonia is NH3. Derivative of ammonia means what? When one of these hydrogen you replace by any alkyl group R, then you'll get RNH2. If two hydrogen you replace, then you'll get by R2NH. Three hydrogen you replace, you'll get R3N. This is 2. Okay. So when nitrogen, this nitrogen contains two hydrogen or one alkyl group, then it is 1 degree amine. Okay. When the nitrogen contains two alkyl group, it is 2 degree amine. When it contains three alkyl group, it is 3 degree amine. Okay, so all these 1 degree, 2 degree, 3 degree amines are functional isomers of each other. You see example here. Suppose if I write down this example, CH3CH2 under this only, under amines only, CH3CH2, CH2NH2, two hydrogen here with one lone pair. Another example, if I write CH3CH2, NHCH3, and one more example will write CH3N, CH3CH3. In all these examples, you see the molecular formula of this will be what? 1, 2, 3 carbon. How many hydrogen? Sorry, how many hydrogen we have? C3, 3, 5, 7, 9, H9, and N. C3H9N. If you calculate the molecular formula of this, it is also C3H9N. And for this one also C3H9N. So this is 1 degree. This is 1 degree amine. Primary amine we also call it as second degree amine, secondary amine, or 3 degree amine, or tertiary amine. Okay, so these three molecules are functional isomers of each other. Molecular formula is same, 1 degree, 2 degree, 3 degree amine are functional isomers of each other. Okay, what about these two? You tell me whether these are functional isomers or not. CS3, H, and CS3. One thing also you see here, 1 degree, 2 degree, 3 degree amines are functional isomers. 1 degree and 1 degree amines are not functional isomers. 1 degree, 2 degree maybe, 2 degree, 3 degree maybe. Means different degree we should have. So is this functional isomers or not, these two? And one more if I give you, NCH3 and H here. N, H, and H. Tell me. No, CN is not an amine, Sridham. CN is cyano group, cyanide. Okay. We will discuss this tomorrow. Okay. CN is nitrile also. Yes. In IPSC name, we'll write nitrile also. Cyano group, cyanide group, nitrile. Tell me this one. These two are functional isomers or not? These two. See, this nitrogen is 3 degree and this nitrogen is 2 degree. Nitrogen contains one hydrogen, you see, nitrogen contains one hydrogen, 2 degree. No hydrogen, then 3 degree. So here we do not have hydrogen with nitrogen, right? So these two are functional isomers or not? First one, Niranjan is saying first one is functional, second one is no. Yes, no. Okay. So this one, obviously it is functional isomers. Yes. For this one, the molecular formula is not same, right? You see the molecular formula is not same. So these two compounds are not identical, not same compounds, not identical compounds. And when the molecular formula itself is not same, we cannot define isomers. Correct? That's the thing. But what happens, Sukirt, if I if I write down one more molecule like this? Now tell me. You have to compare this A and this B. Is these two are functional isomers? Aryaman is saying yes. Shravan, yes. Sukirt, not functional. Sushant is saying yes. Bharat is saying yes. Bharat, what happened to Sukirt? Okay, now Sukirt got it. Everyone's saying yes. Okay, functional. Fine. So you see, because the molecular formula now it is same, right? And this nitrogen is 1 degree and this one is 2 degree. How do you identify primary and secondary amine? Just you check the number of hydrogen attached with the nitrogen. If it is 2, 1 degree. If it is 1, 2 degree, no hydrogen, 3 degree. Okay, 1 and 2 degree. Anyways, so chalo, we'll move on. Next example we have the fifth one. See, all these examples you have to memorize which all functional group shows functional isomers. Okay, so you have to memorize. Sometimes they ask this question directly in the objective. Which one of these pair of these functional group does not show functional isomers or show functional isomers like that? Okay. The next one, probably the fifth one we have, that is carboxylic acid and esters. Okay, so first of all, let me tell you, carboxylic acid, I have done this in HSR, but RNR I'll do it tomorrow. Carboxylic acid is this group. When you have COOH group present, then this is carboxylic acid, which can write it as like this: C double bond O and OH. If you know this, fine. I'm just giving you this information. Ester is this. If this H you replace by alkyl group, C double bond OR, then it is ester. Okay, so these two group also shows functional isomers. Okay, for example, you see, if I write down this compound, that is CH3 C double bond OH. The IUPAC name of this one will be 1,2-ethanoic acid. IUPAC name of this. I will do this tomorrow. Okay, so this Rajinagar guys, you don't get panic if you're not getting it. Okay, if you're getting it, it's fine. IUPAC name is ethanoic acid. Okay, common name is acetic acid. This is very common acid. You will get it everywhere probably in organic chemistry. So you must remember this name, acetic acid, CH3COOH. but this has nothing to do with the concept we are discussing now. This is one particular compound, and if I write down this one, you see HC double bond O and CH3. This hydrogen I'll substitute here, and CH3 I'll put it here. So obviously you see the molecular formula of these two compounds are same. Now it becomes COOR. So it is nothing but ester. COOH. So it is nothing but carboxylic acid. So this becomes ester, and molecular formula is same. So these two are said to be functional isomers of each other. I hope it is clear. One more example, if I can show you, the example is this OH, and this is double bond O. So this is what? This is COOH acid, and the another example, if I write here, oxygen and CH3. Here we have double bond O. So these two, this one is ester, COOR. This one is ester, and this one is carboxylic acid. Molecular formula you can cross check, it is same. So these two are also functional isomers of each other. Okay, next functional group which shows functional isomerism is this, that is amide. Amide functional group is this, it is C double bond O NH2. This group is amide. Whenever you see this group, the name is amide. Okay, like you write down 1 degree amine, 2 degree amine, 3 degree amine. Similarly, we also write down 1 degree amide, 2 degree amide, 3 degree amide. Right? Everything is same here. Like suppose if I write down the same kind of example, CH3 CH2 CH2 C double bond O NH, like this. So this is 1 degree amide. Nitrogen has 2 hydrogen here, so 1 degree amide. Next one you see CH3 CH2 C double bond O NH CH3. So this is 2 degree amide. And again, if I write down CH3 C double bond O N CH3 and CH3. So this is 3 degree amide, tertiary amide. Okay, so all these 1 degree, 2 degree, 3 degree amides are functional isomers of each other, the same way that we have done for amines. So amide also shows functional isomers, isomerism. Understood? Next one you see 6, 7, whatever the number, you just put it down. Next one is aldehyde and ketone. This is very common. You must have done it. Aldehyde, ketone in 10th class also. So aldehyde and ketones are functional isomers of each other. For example, you see the simple one, CH3 C double bond O CH3 and CH3 CH2 C double bond O H. So aldehyde is what? Aldehyde is CHO group. This group you see. Aldehyde is this group, C double bond O H. This is aldehyde when we have hydrogen present one side. Ketone is when we have C double bond O group present. And here must have some alkyl group, R or R dash, whatever it is. Okay, so aldehyde and ketones are functional isomers of each other, provided when they have same molecular formulas. Next one is cyanides and isocyanides. cyanides and isocyanides. Cyanide is this. It is C triple bond N. This is cyanide. And isocyanide is when you have NC, the coordinate bond N, and this is we have. Okay. Isocyanide is this. See, the meaning of this is this N is attached with the primary chain in isocyanides. In cyanides, carbon will attach with the primary chain. Okay. For example, you see this one CN NC. Okay. You see this nitrogen is attached with this primary chain and this carbon is attached with the primary chain. Okay. So this is what? This is the functional isomers. These two are functional isomers. Okay. These two are functional isomers. You can easily check. You can easily check that the molecular formula is same for this. Okay. Another one you see, I am doing some miscellaneous one also. These thing they will never ask in board exam. Okay. So I am just giving you every possibilities that we have in this. Nitro with nitrite. Nitro with nitrite. Nitro is NO2, N double bond O and O. This is nitro, N double bond O, NO2 in short. Nitrite is ONO, right? This ONO. Oxygen will attach with the parent chain. Here, this nitrogen will attach with the parent chain. For example, you see, if I write down this one, CS3N double bond O and this, and we'll write CS3O N double bond O, this one. Again, you see in these two, the molecular formula is same. So these two are also functional isomers. So nitro and nitrite may also show functional isomerism. Just a second. Hello. Where are you? एक्सिस बैंक एटीएम मिला आपको? एक्सिस बैंक एटीएम? Achha, just a second. Just a second. Ma'am, just a second. Okay, guys, we'll do one thing. That I'll just take a 5 minutes break. Okay, we'll start in. It's 6:35. We'll start in 6:40. Okay, I've got some work. Just 5 minutes break we'll take, and then we'll start in some time. Okay, just type in yes. Hello. Okay, can we start? Are you there? Okay. So nitro and nitrite also shows functional isomers. Okay. Next one you see. Next example is enol. The next one is enol and ketone. See, this enol and ketone means what? En stands for, this En stands for double bond, that is ene, and Ol stands for OH, that is hydroxy group, which is nothing but alcohol. So if I write down this compound, you see CH2 double bond, CH single bond, CH2OH, and this compound CH3 C double bond O, CH3. So this one you see the molecular formula for this will be C3H6O, and for this one it is again C3H6O, right? So this, why we are, this is enol and this is ketone. Enol, why? Because we have double bond, for that it is ene, and OH all. So enol ketone also shows functional isomers. Another example of this, if you see, we have a molecule like this, OH and double bond. So this is enol, right? Enol. And we have this double bond O. Enol and ketone. Molecular formula is same here. So hence it is also functional isomers. Right? The last, next, we have last two also into this. The next one is diene with alkyne. Diene means two double bond present. Okay. If the molecule is this one, and here we have triple bond. These two are also diene and alkyne. Molecular formula is C7H12, and here also it is C7H12. So you see same molecular formula with two double bond in one compound and one triple bond in the another compound. So these two also functional isomers. Okay, so this is it for functional isomers, isomerism. Okay, so all these examples you have to keep in mind for functional isomers. What all compound shows functional isomers. Okay, next in this function also we have one more isomers that we actually count in functional isomers only, and that we call it as ring chain isomers. ring chain isomer. Ring chain isomer, you write down. It is due to it is due to the different modes of linking. One compound will be in the ring form and other one will be in the chain form. For example, you see, if I write down this one CH3CH double bond CH2, and if I write down this with this compound, cyclopropane. If you check, molecular formula is same. One is ring, other one is chain. So this is ring chain isomers. This one you see, CH3C triple bond CH. Right. This will be this. These two are again ring chain isomers. Okay. For butene, but1, this one CH3, CH2, CH double bond, CH2. For this, we can draw this structure. This is also ring chain isomers. Or we can also draw this one. Here we have CH3, CH3, ring chain isomers. So all these are ring chain isomers. Okay. Now, one note you write down here, which is important. One note you write down into this. See, just you listen to me one thing first. Suppose this question is given, right? And in the option ring chain isomers is not mentioned. Okay. Since what we do, this ring chain isomers, we consider it as a special type of functional isomers. Ring chain isomers are the other type of functional isomers only. So if in the option ring chain isomers is not given, then we'll consider this as a functional isomers. Right? Otherwise, if ring chain and functional isomers both are given in the option, then we'll prefer ring chain first. Okay, so ring chain is the specific and more like specific answer we have. But if ring chain isomers is not mentioned in the option, then we'll go with the functional isomers, right? If both have been mentioned, ring chain and functional, then we'll prefer ring chain isomers into this. Okay, that point you write down. If ring chain isomers is not mentioned, if ring chain isomer is not mentioned, then we consider this into functional isomers. Then we consider this into functional isomers. Done? Next one. Write down metamers. Metamers, you write down. It is possible only with polyvalent functional group. What is polyvalent functional group? What is polyvalent functional group? What is polyvalent functional group? Tell me. No, you see, polyvalent functional group means whose valency is more than one. This polyvalent means what? Valency of the functional group is greater or equal to 2. Equal to 2 also we can consider. So metamers only possible when we have polyvalent functional group. For example, you see, example of polyvalent functional group you see, like when you write down ether. Ether is nothing but this. This is what? Ether. It is a polyvalent functional group because it can attach with this side also and this side also. Polyvalent. If you have this ester, this side also it can attach, this side also it can attach. Polyvalent. Amines. Polyvalent. Thioether. Thioether. Polyvalent. Ketone. Polyvalent. Amide, which is C double bond O NH. Polyvalent. Okay. Few examples you see. If I write down this, any halogen group X, fluorine, chlorine, bromine, iodine, OH, right, NH2, all these are monovalent. Why it is monovalent? You see, only one bond is open here. Only from this side only it can attach, right? So all these are monovalent, not polyvalent. Monovalent functional group. So in all these group metamers we can explain. Okay. So in this you write down metamers are the compounds. Metamers are the compounds having metamers are the compound having different group present having different group present across the polyvalent functional group. Having different group present across polyvalent functional group with identical molecular formula. With identical molecular formula. Now with example you will understand this. First one you see. If I write down CH3CH2 O CH2CH3 and CH3O CH2CH2CH3. These two compounds you see. Now in this one, you see, you have to just compare the group which is attached to the polyvalent functional group. One side it is ethyl, other side it is also ethyl. So if this group is different in the other compound, then they are said to be what? Metamers of each other. Like you see, if you compare this group left hand side, it is ethyl here, but here it is what? Methyl. Different group. Right side again it is ethyl, but here it is what? Propyl. Right? So here it is methyl propyl, and here it is ethyl and ethyl. Molecular formula of both the compounds are same. So these two compounds are said to be metamers of each other. Is it clear? Yes or no? This one you see H C double bond O OCH2 CH3, and the another compound if I write CH3 C double bond O OCH3. You see, this is the polyvalent functional group. Polyvalent functional group is this and this. So one side we have hydrogen present, here we have CH3 different. Other side we have ethyl present, here we have methyl different. But molecular formula is same. Okay, I'll repeat just once. We'll do some more examples, Sriram. Just wait. What I said that, like you see this example first, the second one. The polyvalent functional group is this COO. This one. This one I am taking now. COO. So one side of this polyvalent functional group we have hydrogen, and other side we have ethyl. And excuse me. Another example you see, one side we have methyl, and other side we have methyl. You just compare the group on the left hand side and the group on the right hand side one by one. So on the left hand side we have CS3, but here we have hydrogen different. Right hand side we have CS3, here we have C2S, CS2, CS3 different. So these two are also what? These two are metamers of each other. Okay, in this what I explained, this side we have ethyl, but here we have methyl, here we have ethyl, here we have propyl. But the thing is what? Molecular formula must be same. So if you compare the molecular formula of this one and this one, it is same, this one and this one, it is same. That's why these are metamers of each other. Okay, what about this one? These are metamers or not? Oh, sorry, this one is not there. These are metamers, yes or no? Yeah, you can say. This is also metamers. Now, one more example, I'll see the last one. These are metamers, yes or no? Metamers, yes or no? Tell me. These are metamers, right? Okay, every one of you are saying yes. Now, tell me one more thing here. What is the IUPAC name of this and this? IUPAC name, you tell me. So the first one is 3-pentanone and the second one is 2-pentanone. And this is 2-pentanone, right? Now, what do you understand by this when you write 3 and 2? When you write 3 and 2, it means the position of keto group is different. Fine. Position of keto group is different. It means it can be positional isomers also. Why can't we take this as positional isomers? Can we say it? Yeah. So if the position of keto group, you understand my question? The position of keto group is different in both the compound, then we can consider this as positional isomers also. Right? Okay, so the point here is what? Now you listen to me. Now you listen to me carefully. Whenever you have polyfunctional group attached to different groups on the other side, then we always prefer to say metamers, not positional isomers. Okay, so for this compound, suppose if the options are given, first is chain, second is position, third one is metamers, and fourth one is ring chain, suppose like this. There are four options given, and what kind of isomers these two compounds shows, then the answer we always go with metamerism, not or metamers, not position isomers. Whenever metamers, like we have in the case of ring chain and functional isomers, if ring chain is mentioned, we'll consider ring chain, otherwise functional, right? So metamers, whenever the polyvalent functional group attached with two different what we say uh, groups, right? Then we always consider this as the metamers, not positional isomers. Okay, okay. But second case, if you imagine, if this option is not given, right? If metamers is given, we'll go with this only. If this option is not given and we have some other option here, none of these or something like that, then we can choose position isomers. Is it clear? So basically, we'll prefer metamers. If metamers is not mentioned, then we can go with position isomers. Understood? Tell me. Okay, so we are done with structural isomerism today. In this, we are left with tautomerism or tautomers. Okay, so we'll discuss it later when we do some reaction mechanism. Okay, some reactions thing we'll discuss this later. So this tautomers, you let it be now. Tautomers in which both compounds may exist in dynamic equilibrium. The isomers exist in dynamic equilibrium. So this you will not understand this now. So just you let it be for other classes. Right. Now, the next thing we have to discuss here is stereochemistry, right? Okay, just you solve these questions first. Okay. Okay, so we'll see the question. I'll just send you. We are not getting it now. Anyways, so next one you write down stereochemistry. Not stereochemistry, stereoisomerism. Stereoisomerism. Okay. You see, stereoisomerism is what? It is due to the change in property of the molecule due to the relative position of atoms or groups present in the space. Right. So we are talking about, yeah, tautomers is okay. This is right. Tautomers is what ketoenol tautomerism. We have 4 or 5 examples into that. Okay, so there are many things to discuss into that. So that's why we are not doing it now. And for that, you require basic idea of reactions. Okay, so we'll do it later. Now you see here stereoisomerism and why it is important. Like one example, I'll give you here. First of all, the difference in stereo and structural isomerism is what? In structural isomerism, we'll discuss the molecules or the relative position of molecules in the plane, in a given plane in which the molecule is, right? But you see, if I write down one compound, okay, first you write down the definition of this. Write down stereoisomerism. Write down stereoisomerism is the study of stereoisomerism is the study of is the study of the change in the physical and chemical properties of any molecule, the change in physical and chemical properties of any molecule due to the change in position or change in relative position, you write down, due to the change in relative position change in relative position of the atoms or groups, change in relative position of the atoms or groups attached to it in three-dimensional space. In three-dimensional space. Okay. Now you see, before going into so detail of all these concepts, first of all, we'll try to understand what is the use of this stereochemistry we have, or stereoisomerism. Let me give you one example here. That is, the name of the compound is platin. 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 The formula of this is Pt NH3 whole twice and Cl2. Right? This is platin. Now the structure of platin is this. We will discuss this. Actually, we are talking about optical isomerism and all, because all this comes under stereo isomerism only. So we'll discuss this in detail later on. But right now I'm just giving you the idea of why this is important and why we are studying this. See, the structure of this compound is this, and this is the information I am giving you. Don't put your brain now into it. Okay, we will discuss this and then you will understand. Okay, now you just keep in mind that the structure of this compound is like this. It is a square planar geometry. Cl and Cl. Now in this molecule you see, this is the platinum is a central molecule and it is attached with two ammonia and two chlorine, and here also the same thing we have. But the difference in these two structure is what? In one structure, the first one, the two ammonia group is present at 90 degree from each other, mutually 90 degree, right? And here it is at 180 degree, correct? So now you see, when the identical group present at 90 degree from each other, then this compound is cis, and we call it as cisplatin. Don't you like think on it that how do we get this, what is cis and all, what is 90 and 180? Just you write it down. Okay, if you do not understand this, why it is cis and why it is transplatin, then we will discuss this. Okay, so you don't panic now. Just to understand, when the NH3 is present at diagonally opposite to each other, it is trans, and when it is at 90 degree from each other, it is cis. Okay, so this is basically the two isomers of this compound we have, platin, right? It exists in two different form. One is cisplatin, other one is transplatin. Now, what is the difference in these two structure we have? The only difference is the relative position of these molecules, right? NH3 and Cl, right? The relative position of these molecules. Okay. So in this, the relative position is different. So what happens with this? The property of the molecule changes, and which is nothing but the isomers we have. When you change the molecule relative position of the molecule in three-dimensional space, the property of the molecule also changes. And this property changes to an extent through which one of this form, yes, cis and trans. Okay, so we are not going into dipole moment and all. Okay, so one of this form, you see here, this question they have asked many times in NEET exam also. This cisplatin is used in cancer therapy as a drug, cancer drug we also call it as. But this is not at all useful for cancer therapy. So the point I'm trying to make here it is what? The molecular formula is same for both the compound. What we are changing, we are only changing the relative position of these molecules, right? Here it is at 90 degree, here it is at 180 degree. And with change in this relative position, the property of the molecule changes to such an extent so that one form is useful in a cancer therapy and other form is not useful, right? So that is how the importance of stereochemistry we have. This all this study of properties of this molecule we do under stereochemistry only. So that's why all these pharmaceutical industry we have, they hire uh, they hire all these uh, PhD scholar in chemistry, organic chemistry and all. Okay, so the point here is what, that just we are changing the relative position of this molecule, and one form is applicable or one form is useful for cancer therapy, other form is not. So you can understand till what extent the properties of the molecule changes. That's why in all these pharmaceutical industry that we have, whenever they are going to produce a drug or new drug or medicine, first of all they study the stereo aspect of that particular drug, right? Stereo aspect means what? Stereo study means what? The relative position of the molecule when changes, how the property of the molecule changes. Understood? So the point here is what? All these things will do under this stereoisomerism. Difference in stereo and structural what we have. In structural we have the connectivity is different, but here the relative position in three-dimensional space is different. Right? Now the first thing, this is what the importance of this particular topic we have in our life. Okay, and the first thing we are going to understand here, or first type of isomerism we are going to see, that is geometrical isomerism. Geometrical isomerism. Okay, now one thing you tell me, if I write down two structure here, one is suppose C double bond C, and here we have suppose anything, chlorine, hydrogen, and this side we have hydrogen and chlorine. This one and C double bond C, we have hydrogen, chlorine, hydrogen, chlorine. First of all, these two compounds are same or different? That you answer me. And one more example I'll write down. This one, these two. So these two compounds are same or different? These two compounds are same or different? Tell me that. Yeah, this we are doing under configurational isomerism, correct? The first two, These two are same or different, or these two are same or different? First is different, second is same. Anyone else? First one is different. Okay. See why these first two compounds are different, because here the free rotation is hindered here because of the pi bond here. Okay. How this pi bond forms? This carbon carbon has sigma bond, and this p orbital, when overlaps laterally, right, this kind of overlap forms pi bond. And if this rotation is hindered, because we cannot rotate this particular carbon by along this axis like this, we cannot rotate. If you rotate, this bond will break, right? And we cannot break the molecule here, right? So here what happens, what we say, whenever double bond is present, so the free rotation is hindered, or free rotation is not possible or hindered. And in these two, since you have sigma bond, so we can easily rotate this and we'll get this. Suppose this carbon, if you rotate like this, if you rotate, the hydrogen will come here, chlorine will go down, and we'll get this. These two compounds are actually the same compound we have, but these two compounds are different. Different in the sense what? When you try to find out the dipole moment, stability and all, okay, you will get different stability of these two compounds and different dipole moment also. See what I said, Ashutosh, this pi bond, if suppose this pi bond is not there, only single bond is there, carbon carbon single bond, right? So one of these carbon we can rotate along this axis, no, like this we can rotate, since there is only one bond is present here. But this kind of rotation is not possible when we have pi bond present. But in this case, if you try to rotate this molecule along this, then obviously this bond you have to break, this pi bond you have to break, right? So in whenever you have pi bond present, then this kind of free rotation is not possible, and we say the free rotation is hindered over there. And when the free rotation is hindered, right, when the free rotation is hindered, so this, from this molecule we cannot get this molecule. The entire molecule we can flip, but we cannot flip one particular carbon, any of these carbon we cannot flip because of the double bond. But here what happens, we have only one bond present here like this. So this carbon you can easily rotate along this line like this. One rotation you do 180-degree or by some angle, this chlorine will come here, hydrogen will come here. So with this rotation, you'll get this compound only which is there in the top, right? So that's why these two compounds are similar compound and these two compounds are different compound. Okay, so geometrical isomerism is possible when we have this kind of arrangement. Okay, there are other possibility also, like when we have ring and double bond within the ring. So basically, geometrical isomers or isomerism possible because of double bond, first case, because of ring, second case, and because of double bond inside the ring. Double bond inside the ring. Okay, in these three cases, geometrical isomerism is possible, right? And now in this, we also, since these two compounds are different, like we said, these two compounds are different. Now, what is the name of this compound? You will write IUPAC name of this will be what? What is the IUPAC name of this compound? This one. What is the IUPAC name of this one? Tell me, what is the IUPAC name? 1,2-dichloroethene. 1,2-dichloroethene. Okay. So this one is 1,2-dichloroethene. What about this one? Is it also 1, 2 dichloroethene? Yes. Both compound are 1, 2 dichloroethene only. Yes or no? No, I'm asking you. Both name is same only 1, 2 dichloroethene. Yes or no? Correct. But actually the properties and these two molecules are different in nature. Just now we have discussed. These two molecules having different nature. But according to IUPAC, the name of both compound is 1,2-dichloroethene. Now when you go reverse of this, and if I ask you, draw the structure of 1,2-dichloroethene, then you will draw either this one, some of you will draw this one, some of you will draw this one, right? Correct. But since both compounds are different, so how do you know that we are talking about which compound? Here we have the problem in IUPAC, right? IUPAC given us this rule, and according to this rule, the name of both compound is 1,2-dichloroethene. So how do we differentiate this? That whether we are talking about this compound or this compound? That's the question now. So for that we are using two different term here, and that term is cis and trans. Cis and trans. Now ENZ is different in different case ENZ we use. ENZ we use when we have, we'll discuss when we use ENZ. So we have cis and trans, we have ENZ, we have syn and anti also. Okay. So that you let it be, you don't go there. Now we will stop here only. Okay, we don't have that much time. Okay. Now next class we'll try to understand how to uh, find out whether geometrical isomerism is possible or not, and when do we write down cis and when do we write down trans for a given compound. Understood? So let me give you one thing. This particular example is cis form and this one is trans form. So when I write down the name of this compound, I will write cis 1,2-dichloroethene, and for this we'll write trans 1,2-dichloroethene. So when you use this cis and trans term, you will actually understand that whether this chlorine, the position of chlorine is what. We cannot discuss this Advait now, we don't have that much time. Okay, when we use cis and trans term, we will discuss this in the next class. Yeah, we will finish nomenclature, and if time permits we will continue with this tomorrow. Okay, so we'll stop here only. Okay. Okay, chalo, thank you.